Okay, so this will be the prep video for section 5.4, the definite integral. And so let me start drawing some sketches. All right, so let's say that we have just some curve. And we would like to find the area under the curve. Well, we know if it's a triangle, we have formulas. A circle, we have formulas. Squares, rectangles, we have formulas for those. But this clearly doesn't fit any of those. So let's say I wanted to find the area from here, let's call that A, to here. So we don't have a formula for that, but maybe we could sort of estimate it. So maybe if we broke this into 4 pieces, and we could make a triangle. You know, so here, we draw in. We could kind of make some triangles. So let's just maybe go kind of through the middle. So here's not a triangle, a rectangle. And then maybe, you know, through here. And then maybe this one is more like that. And maybe this one's more like that. And so we see that we actually have this columns of rectangles, and we could add up the area. So what do we know? We know that this width here, let's call that delta x. And what is the height? Well, it's going to be a function of that. And so we'll just call that x sub I, meaning the first one, this would be f of x sub 1, x sub 2, x sub 3, you know, so just the point here where it crosses the curve. Okay, so we could then add up the area just by adding up these columns. So what would that be? We'll use a symbol in math. It's this. It's a capital sigma, Greek letter. And this just means add up. Sigma s sum add up. So what are we going to add up? We're going to add up the area of each rectangle. So the area is going to be the length or the height times the width. So we'll have, like, let me write it this way first. F of x sub 1 times delta x plus f of x sub 2, the second height, times that same width, because we made the width the same, plus the third, plus the fourth. But now in math, we often like to try and simplify things a little bit. So let's see if we can write this in a neater way. So here we'll introduce that symbol, sigma, means add up the following. And we notice that these look exactly the same. It's just that this goes from an x sub 1, x sub 2, x sub 3, x sub 4. So we're going to consolidate that down and say it's going to be the height at whatever that x value is. And then the width is the same, delta x. So we're going to let I start at 1 and go all the way up to 4. So f of x sub 1 times delta x, and then f of x sub 2 times delta x, all the way up to 4. Okay, so that would be the area for this. Now, that might be a reasonable estimate. It might be okay. You might figure if we could divide this into more pieces, that each piece could be a little bit closer to the curve, and the answer might be a little bit more accurate. And we could keep subdividing and subdividing and subdividing. In fact, we could let that delta x go all the way down to 0. So what happens when we do that? This is a limiting function. We've talked about limits before. So let's back up and make a little more space. So let's look at what would happen then. We could write this area as the limit as delta x gets really small. So we're going to let these get really skinnier, 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 skinnier. So they're almost just like a stack of lines of this. Okay. And it turns out that if you think about this, if delta x is going to 0, we've run into that before. Remember when we were doing differentials? And we said, well, we can let delta x and dx be about the same. When delta x goes to 0, this becomes a dx. And this sum becomes the integral. And then we just have f of x. Where do we go? From A to B. Okay, so we're going to start at A, and we're going to add up all of these essentially lines, right? A height times a width that's so skinny that it's really just a line. And we're going to start at A and add up all the way to B. But we've done this. This is integrals. This is antiderivative, so we know how to do this. So let's look at some general rules. Okay, so the first thing we need is, we need to talk about area. So I'm talking about area here, and the one that I drew had everything above the x-axis. We need to be a little bit careful about that. So let me draw another one. So let's say that this is A, that's 0, that's B, and that number x is C. And then we'll name these. We'll call this area capital A, capital B, capital C. Now the thing we need to be careful about is that we know that the actual area, I mean this area is always positive, right? We know that. So I actually know a few numbers here. In this particular example, we know that the area A is 2.33, the area B is 10.67, and the area C is 5.63. All right, so let's just say those are what the areas are. Maybe not quite drawn to scale. The thing that's important to remember about how we develop this is that this f of x can be negative, right? Any function can be below the x-axis. So when we add up these heights, if it's below the x-axis, it's like we're adding a negative bit, because this will be a negative number. So the thing that we need to think about is that integrals are really signed area. Let me write that down. An integral represents signed area. And so what does that mean? That means that the area is, if the shaded portion is below the x-axis, the integral is going to be negative. And if the shaded area is above the x-axis, where you're doing the integral, then it will be positive. So I'm going to put area in quotes here, because we know area is always positive, but in this case, the shaded region, if it's below the x-axis, it's negative. And if it's above the x-axis, it's going to be positive. Okay, so let's do some examples using this setup. Try my red marker, maybe it's a little bit better. Okay, so let's look at this. What if we wanted to find the integral from a to 0 of f of x dx, where this is f of x over here. So from a to 0, here's our point A, and we're going to add up all the way till we get to x equals 0. Well, that means we've just added up this region that's called A. So we know that that will be the value of the integral, but because it's below the x-axis, it will be negative. So the answer to this integral would be negative 2.33. I could look at the integral from 0 to b of the same function. Okay, so that starts here 0, and we're going to add up, we're going to integrate all the way through to b. So we're going to get this whole capital B region. It's above the x-axis, so the answer is 10.67. All right, let's look at the integral from b to c. So we start here at b, and we add up all the way till we get to x equals c, so that's that whole c region, 5.63, but because it's below the x-axis, it's negative. So negative 5.63. So again, if the region is below the x-axis, the integral will be negative. The area is always positive, we know that, but the integral of anything below the x-axis will be negative. So what about this one? What if I integrated from 0 to c? Well, that says start adding up from here at 0 and go all the way up to c. So I'm going to start adding, I'm getting more and more, I'm adding positive, 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 and now I start adding negative. I just keep right on adding. It's just that this part up here is positive and that part's negative. So once I get through all the positive part, that's 10.67. And then I start adding in negative, and so I'm actually going to subtract that value, minus 5.63. So my final answer here will be positive 5.04. Okay, so that starts to lead us to something interesting, which is that integrals are a sum. We saw that from how we defined it, but you can add all the way through no matter what the function is doing. It can be above the axis, below the axis. You're just adding straight on through. Okay, so let's write down some rules. We'll have a set of integration rules, and then we'll do some more integrals. Okay, so just like we have derivative rules, we know we have the three different functions that we've dealt with for both integrals and, for derivatives and integrals. So we have power functions, log functions, and exponential functions. And then in addition, there's always something we write, which is constants, multiplication by a constant carries through, and addition and subtraction carry through. And that's true for integrals as well. So let's start with some integral rules here. So I'm going to start with that one just because that one, it's true for limits, derivatives, antiderivatives, integrals, definite integrals, everything. So multiplication by a constant carries through. So what would that look like? That would say if we integrated from a to b and we multiplied the function by some number k. That means that k, I can pull out front and just multiply through like I normally do. So you can write it this way. Multiplication carries through. We also know the same about addition and subtraction. They also carry through, so if you've got, let me write it this way, from a to b, and you've got some f of x, and either you have added or subtracted, that's what that means, some other function, all of that is integrated with respect to x. You can pull apart the functions and deal with them separately. So you can write this as the integral from a to b of f of x dx, plus or minus, whatever you had here, times the integral from a to b of g of x. So multiplication carries through, addition, subtraction carry through. And then we have some other rules. Some make a lot of sense. Others, there's one that to me seems a little bit odd, but it's a rule. The first one is if I go and integrate from a to a, what does that mean? That means I start at one point and I don't go anywhere. So how much area could you possibly have added up? None at all. So that's the answer. So if you integrate from a to a, any number and then the same number, the integral is 0 because you've got no area to add. And then we have, this is the one that I think is a little bit strange, but we'll throw it in there. If you integrate from b to a, we have been going a to b, kind of left to right. If I went backwards, it's negative. It just introduces a negative sign. So you're adding kind of in a forward direction, so if you start adding in a backwards direction, we just introduce a negative sign. And then the last one is, just like in that last example where we had some positive area, and then we kept adding, and we kept adding in some negative values as well, we can actually split apart integrals. So we can write, if we integrated from a to c, and there was some breakpoint in the middle that was handy for us, for one reason or another, we could break this apart and go from a to b, and then add to that the remainder of the x interval from b to c. So it's just saying that you can break it apart into kind of component side-by-side pieces. So this is our set of integration rules. So let's look at an example where we're going to use those. So we'll start with this. Integral from 0 to 2 of x dx equals 2. So these are just, we'll look at how to do these shortly, but for now let's just write them. Actually, we've already done these, I guess. No, we haven't. We'll do these in class. But let's just go ahead and write down. These are just what the answers are. They don't come from nowhere. It's not magic. We'll derive these in class next time. And so we also know from 0 to 2 of x squared dx is 8/3. And then lastly, from 2 to 3, the integral of x squared dx is 19/3. So now the question is, can we, using these rules, combining these with something we know here, can we get an answer? So let's look at this first one. The integral from 0 to 2 of 6x squared dx. Okay, well, what do I have? I have an integral of x squared dx. So what can I do with that 6? Well, multiplication by a constant carries through. So I can just, if you want to rewrite this step, you can pull it out front. But now this piece, I know exactly. So I can simply write 6 times the answer to that, 8/3. All right, so this is not the example I have in the notes. I actually moved from 2 to 3 instead, but it works the same way. So I'm going to suggest to you here with doing fractions, always cancel first. This is like 6/1. The 6 and the 3 cancel, so we get an answer of 16. So always, when you can, cancel first before multiplying. All right, here's another one. From 0 to 2 of 9x squared minus 4x dx. Okay, again, we know the integral from 0 to 2 of x squared, and we know the answer for x. I've multiplied by 9 and subtracted and then multiplied by 4. All of those things carry through. So you could rewrite it all this way, breaking it apart into its component pieces. Let's do that this first time. So I'm going to say that I'm going to break the two pieces apart because I know subtraction carries through. And then I'm going to pull the 9 and the 4 out front because I know multiplication carries through. So I can write it finally this way. But then I know this piece and I know this. Oops, sorry, this piece. So I can write down the answer. So the answer would be 9 times the value of this, which is 8/3, minus 4 times the value of this, which is 2. Again, I'm going to recommend that you deal with the fraction, do the canceling first. So you get 24 minus 8, 16. Again, isn't that interesting? Okay, so let's look at this one. What if I integrated from 2 to 0 of 9x squared minus 4x all dx? Well, that's sort of out of order, so I could rewrite it this way. Negative from 0 to 2 of this. But we already did this one. That's the one we just did. So the answer to this one is exactly the answer to the previous one, minus 16. Because the only thing different is that we integrated in the opposite order. So just remember, when you integrate backwards, you introduce a negative sign. Okay? Yes. All right, 2 more. What about this one? Negative 2 to negative 2 of 3x dx. Well, I could pull the 3 out because multiplication carries through, but I don't know anything there are no negative 2's up here for limits, so I don't know anything about that. But I've gone from negative 2 to negative 2. Have I gone anywhere? I've added up area for precisely no time at all. So this answer is simply 0. And then lastly, our last example, from 0 to 3 of 12x squared dx. Okay, the 12 will carry through. I know how to handle that. 0 to 3. I have 0 to 2. Let's see, x squared, 0 to 2 and 2 to 3. I don't have 0 to 3, but because these butt up against each other, if I add this one to this one, I'll go all the way from 0 through 2, all the way to 3. So I can simply write this as 0 to 2, 12x squared dx, plus from 2 to 3, the integral of 12x squared dx. Okay, so now I know that I have 12 times that number, because from 0 to 2 of x squared, 8/3, plus 12 times this one, 19/3. And I'm going to suggest something here. You could multiply this all out. One thing that I like to do is to group my thirds. I'm going to pull a 12 out of everything. And then I'll have 8 thirds plus 19 thirds. Well, 8 thirds and 19 thirds is 27 thirds. Don't multiply out. We know this. 12 over 3 is 4. Or we could say 12 times 9. That also, 12 times 9. However you want to think about it. Either way, 108. So you're going to end up with a lot of fractions when you start doing integrals, lots of thirds, because anytime we integrate an x squared, we're going to get a 1/3 x cubed. So lots of thirds. I recommend grouping all, kind of like gathering like terms. Gather all the thirds together, all the halves together, all the fourths together, add them up first, because a lot of times things will cancel or at least simplify before you start adding the different fractions together. Okay, so I think that's it.